Hi everyone, this will be a short video all about proofs. From the survey, it looked like these were the three areas that we could use the most help: hypothetical rules, derived rules, and theorems. And so what I'll do is I'll briefly discuss each one, and then we will use two different examples to see these in action. First up are hypothetical rules. So you should be familiar with the 10 basic rules. These 10 basic rules are the foundation for our propositional logic system. They allow us to use proofs or to prove validity of any argument within the system. And so they are crucial. They are very important. 8 of them are pretty self-explanatory, pretty, face value, but 2 of them take a little bit more work. And those 2 are our hypothetical rules, negation introduction, and conditional introduction. So we'll go through both of them and what they mean, but just a reminder, or we'll see them in action in just a minute. But just a reminder, with negation introduction, imagine that you are talking with a friend, and that friend is telling you something that you are not buying, right? But you don't have any proof to prove them wrong right away. So what you'll want to do is you'll want to be like, okay, let's assume that you're right. Let's say that your friend is saying, you know what, Ava is going to the party. But you know that Ava's not going to the party, you just can't prove it. And so what you do is you say to your friend, let's pretend like Ava does go to the party. Well, what would happen in that case? And then you go through this whole list of things that would happen, and in the end you come to some kind of contradiction, some kind of P and not P. Something that seems absurd or crazy. And so what that allows you to do is that allows you to say that it's not the case that Ava is going to the party, right? Because you're if she did go to the party, then this crazy thing would happen. That's absurd. That's insane. That can't happen. So I know she's not going to the party. For a conditional introduction, it has a similar vibe here. Again, this is a proof within a proof, right? It's like a dream within a dream. Nothing that happens in these subproofs are things that we know for sure. It's just saying, look, if we had this information or if we knew this thing, then we would come across this other thing. And so let's say that you want to prove that if Ava goes to the party, then Brandy will go to the party. Okay, but you don't have that information quite yet, but you feel with the clues you've gotten about who's going to this party or not, that's a conclusion you could make, right? So what you'll do is you will pretend like Ava's going to the party. And again, you don't know whether Ava's actually going to the party, right? You're just saying, let's pretend like she does. And then you find out all these things happen. And then, one of them leads to Brandy going to the party as well. So look, this is a dream within a dream. It's a sub-proof there, right? So the real proof is going on over here. We're indenting. And so what you haven't shown that Ava or Brandy's actually going to the party, but what you have shown is that if Ava does go to the party, then Brandy will. All right, so you're allowed to deduce that. So for both of our hypothetical rules, remember that term hypothetical, right? It's not information it's not concrete information we have, but it's let's pretend in this scenario that this thing happens. What will that tell us? Okay, it's a hypothetical. My guess is that you have been in a situation, conversations with people where you have used hypotheticals before. Think of those situations. Next up are our derived rules. These are another set of rules. These are not the 10 basic rules. So here they are. Our derived rules are basically shortcuts, right? So any of these that we see here, modus tollens, hypothetical syllogism, any of these can be proved with the 10 basic rules. All right, those 10 basic rules are all that we need. But the thing is that sometimes we are hey, here's a shortcut we could take. And we know that it's valid because people have proved this before. So it's a valid move. It's basically this common pattern that comes up a lot. Let's just make a rule out of it. So basically you can think of the derived rules as shortcuts. They allow us to do the work that our 10 basic rules justify, right? We could take the long road. It's like doing short division, right? You could do the long division, but if you know a few tricks, you can just skip some of those and you know that you're going to get to the right answer if you do it correctly. All right, so all of these derived rules are ones that we can prove with the 10 basic rules, but they're basically shortcuts. And when we went over this in the class lecture, what I did is I presented them to you all in terms of like P's and Q's, right? Because I know that this is a lot of wordy stuff that we have over, right? Like these explanations right there, right? So think of them like this, right? If you have modus tollens tells us if we have a conditional and then we have the negation of the consequent, we can infer the negation of the antecedent. All right, so my suggestion for these derived rules would be to focus on how they appear in proofs rather than focusing on like how we justify the derived rules themselves. Basically, a good way to function here is just to say, hey, just trust me. These are all valid moves. So you don't need to worry about like why we can use them. I mean, maybe in a different class that would be more important, but for our purposes, just be able to recognize them, right? So if you see a disjunction, P or Q, and then you also see the negation of one side of that disjunction, we can infer the other side of that disjunction, and this is disjunctive syllogism. All right, so in class we spent today talking about all of these. I have some other ways to remember them and examples of them, but that's the role that derived rules play. And the more comfortable you get with these patterns, the quicker you will be to recognize them when they come up in arguments. Last but not least, we will go over a theorem today. That will be the second example that I have for you all. So a theorem is basically it's like the conclusion of an argument by itself, but like we don't have any premises. So remember, you can't have a conclusion if it's not an argument. And it can only be an argument if you have at least one premise and a conclusion, right? There's no inference happening here. So theorems, if you remember, they are the same thing as our tautologies from chapter 3, right? And a tautology, if we put it into a truth table, we would find that it is true all the way down that truth table, right? So theorems are the same set of statements in the world, but when we call it a theorem, it's because we're able to prove it with only using our rules and not using any assumptions. So we will use the second example to go over what a theorem is. Okay, so here is our first example of an argument, and we will do a proof for it. This is not a theorem because we have a premise. So the first thing we're going to do is we're going to list that premise. If A, then if B, then C. And as you've heard from me many times before by now, what I like to do is I like to put the conclusion just off to the side, just so that I don't forget about it. Right? Because my point is, I always want this to be directing everything I do in this proof. I don't want to forget the whole reason why we're here, right? This is the goal. So there is the setup. I'm going to put A right here for assumption, right? Because it's one of my premises. It's called an assumption. All right, so the first thing we do is we look to that conclusion and we say, how can I get to that conclusion? That's my whole goal here. And I see that the main operator is a conditional. So what we do when we see the main operator is a conditional, if nothing else pops up, right? So give yourself a few seconds, like 30 or 60 seconds, to look at the argument, look at the forest rather than the trees, and think about whether anything pops up. Like if it happens to be an easy argument, and you can just use maybe a few of the basic rules to prove it, then that should guide you, right? Like jump in, try and figure it out that way. But if that's not the case, and you look at this and you're like, whoa, that's kind of a complicated conclusion, look at the main operator. It's a conditional. So what are we going to do? We're going to do a conditional proof, because the last thing I'm going to do in this proof is I'm going to introduce that conditional, right? And as soon as I do that, I'm totally done, right? So as soon as I am able to prove that conditional, I'll be done. So in a conditional proof, what you need to do is you assume the antecedent and show that it leads to the consequent. So I'm going to assume the antecedent. We see it right there. So this is if not B, then not A. And then I'm going to show that it leads to that consequent. So I want to make sure that I note that I'm going to be doing a subproof, a hypothesis for conditional introduction. All right. So when I look at that consequent though, and my goal now is to get that consequent if A then C, and I look at my premise and even my hypothesis there's nothing that like speaks to me, right? I don't see any way right now that I could get if A then C. So what do? I look at that consequent because that's what I'm focused on proving right now. And I look at its main operator. Oh, that's a conditional. Going to do a conditional proof. So I'm actually going to do a nested subproof in here. So now I'm going to assume A, another hypothesis for conditional introduction. And I'm going to show that I can get C out of there, right? If I can show if A then C, then I'll show that if not A then B, or sorry, if not B then not A leads me to if A then C. Okay, so here's how the rest of it will go then. Now we have A. That doesn't, well, it could help me a little bit. Like for example, I can use A to get if B then C. Sure, why not? That's lines 1 and 3, conditional elimination, okay? So that works, but what I really want to get is C out of there, okay? So I don't know exactly how I'll do that right now, right? So I'm looking at saying, hey, I need to get just C by itself on a line within this nested subproof. So if I look around and I'm like, well, I don't have C anywhere except I have it as that consequent of line 4. In order to get that, I'll need to have the antecedent of line 4 because that allows me to use modus ponens or conditional elimination to get C out of there. But I don't have B. So how could I get it? Well, if I look at line 2, I note that I have not B there as an antecedent, but what I'd really like to have is just B by itself as a consequent, right? No negation with it. So what I can do, hopefully you've seen this coming, is I can say if A then B, and that is with one of my equivalence rules, that is transposition. So that is line 2, transposition, and that allows me to say if A then B. Now that I have that, I can use lines 3 and 5 together to give me B, 3 and 5, that's conditional elimination. So now I have B, which will allow me to get C because that is line 4 and 6 together, conditional elimination. And so now what I've just shown is that if I had A, I could get C, right? If I had A, then I could get C. That's lines 3 through 7. And that is a conditional introduction. So look, I've just discharged that line, that hypothesis. And so now I'm working backwards and I need to discharge that one because what I've really shown is that if I had if not B, then not A, right? Then it would lead me to have if A, then C. And that is lines 2 through 8, conditional introduction. So I've just discharged that and I've shown the whole conclusion, so I'm done. We're almost ready for the next one, but I noticed that I'm almost out of time on this video, so I'm going to record another short video for the second example.